Hi guys, welcome to a very low production digital version of our organic chemistry lecture. So today I'm going to write on the dry erase board instead of the chalkboard and make a couple different videos that you can watch to go through the topics in the alcohol chapter that we would have covered today in class if we had had class. So we're going to talk about acidity of alcohols, oxidation and reduction reactions of alcohols, and ways of converting alcohols, that OH group, into a halogen group. We already know a few ways, but we'll learn some better methods in this chapter. And as I go through this, I'm following along on the worksheet that's titled Alcohols. We already did nomenclature on the front side, so if you flip to the second page, that's where we're going to start with the practice problems. And as we get to this, you might want to pause the video, try the problem, and then restart it. So our first topic is acidity of alcohols. Let's get a clean board here. Okay. So I've put a chart on the board a couple times this semester where we talk about the strengths of acids. So the strongest acids that we know of in organic chemistry are those things like hydrochloric acid, hydrobromic acid. They're much stronger than carboxylic acids. And after carboxylic acids, we have a special type of alcohol, the phenol. So when you have an OH group on a benzene ring, if you deprotonate that, we know that that conjugate base has a lot of resonance stabilization. So that makes that an unusually strong acid for an alcohol. Next in line is water, and that's about as acidic as an alcohol. And then of our acidic molecules, our terminal alkynes come at the end here. So if you have a proton on the end of a triple bond, that's very, very weakly acidic. So we saw in the last chapter that to deprotonate a terminal alkyne, you would need a really strong base like sodium amide, NaN2. To deprotonate an alcohol, which we're going to be doing a lot in this chapter, you would use NaH, sodium hydride. And to deprotonate a phenol, because that's more acidic than a normal alcohol, you only need sodium hydroxide. That also works to deprotonate carboxylic acids. So this would be bases to deprotonate. So this is something that we'll want to keep in mind as we get to different synthesis problems, that if we ever need to deprotonate an alcohol, we would use sodium hydride. It turns it into an alkoxide ion. So for example, let's say we have butanol and we add sodium hydride. This H minus, the hydride ion, pulls a proton off of the alcohol. And you're left with something like this. And then the side product is H2 gas, because H minus just pulled off H plus. So there's a good driving force for this reaction. And this is our alcohol, and once we deprotonate it, we call it an alkoxide ion. Okay, so let's try the first problem on the worksheet. Here we're going to use the idea of the acidity of alcohols in order to separate two different molecules from each other. So the question tells us to draw a flowchart for how we would separate cyclopentanol and orthomethylphenol. So at this point, you might want to pause the video and try the problem on your own, and then you can turn it back on and look at how I answer the question. So let's start over here. Okay, so in this problem, first I have to draw the structures of these two molecules. Cyclopentanol is going to be a cyclopentane ring with an alcohol coming off of it. And then orthomethylphenol, on the nomenclature side of the worksheet, we saw that when you have a benzene ring with an OH on it, that's called phenol. And if it says orthomethyl, then that means in the ortho position I have to draw a methyl group. So this is the ortho position, meta position, para position. You can review that on the first page of this worksheet packet if you want, but the ortho position is right here, so I have to draw a methyl group there. Okay, so in my flow chart, these are the two molecules that I'm starting with, and I have to figure out how to separate them. And in lab, we learned that one of the ways that you separate different organic molecules is if you can deprotonate one, then you make it ionic and it will go into the aqueous layer. And so that's exactly what we want to do here. We have a molecule that's just a plain old alcohol, and so it would take a really strong base to deprotonate that, a base like sodium hydride. But over here, we have a phenol. This is a phenol. And so phenols actually have much lower pKa values. They're much more acidic because of the resonance stabilization of a conjugate base. And so if I use sodium hydroxide, I can deprotonate the phenol without deprotonating the alcohol. So I'll use an aqueous solution of sodium hydroxide. Okay, that means there's a lot of water there. And then I'll put some organic solvent in here because I would be doing an extraction. So maybe dichloromethane. That's something we've used in lab before to separate organic from aqueous layers. And then in my flow chart, I'm going to show which way the two layers go. So I'll say that this is the top layer, which in this case, because of densities, would be the water layer, the aqueous layer. And this is going to be my bottom, my organic layer. So in the aqueous layer, we're going to get the phenol, which becomes deprotonated. It's now ionic, and so it becomes water soluble. So it's going to look like a phenol, except the difference is that now that proton, that acidic proton, has been pulled off by the sodium hydroxide. So it's actually going to exist as an ionic compound. And then there's going to be a lot of water in this aqueous layer. The alcohol never got deprotonated. Sodium hydroxide is too weak of a base to deprotonate a plain old alcohol. So the alcohol remains in the dichloromethane layer. And so if you put all of this in a separatory funnel and you separate the two layers, you've now separated your two compounds. It doesn't tell us in the question whether or not we have to isolate the final compounds. Like, this would be enough to separate them. But if I wanted to turn this back into the phenol instead of the deprotonated form, then I would just reprotonate it with hydrochloric acid, an aqueous solution of that. And then that's going to reprotonate our phenol. It's going to make it more organic soluble, so it'll probably precipitate out of the water layer. And then you can do a vacuum filtration. So HCl and then vacuum filter. And our filter cake, the solid that's left on our filter, will be the reprotonated form of this molecule. So that's how we isolate that. And then all the filtrate that passes through the filter will just be, all the little side products will just, right, aqueous layer. That's what comes through the filter. And over here, if we want to isolate our alcohol, we have dichloromethane. It has a very low boiling point. We're just going to evaporate off the dichloromethane. Evaporate off or distill off the dichloromethane. And so in the end, we just have our pure alcohol. No solvent mixed in with it. Okay, so that is the solution to problem 1 on the worksheet that says reaction of alcohols.